Okay, so we're continuing our chapter 15 video lecture. We're going to talk a little bit about the relationship between our hydronium molarity at equilibrium and our initial acid concentration. So looking here, the definition of a percent ionization, we have our hydronium concentration at equilibrium divided by our initial acid times 100 to make it a percent. So let's see how these are related to each other. So we think about increasing the initial concentration of the acid. What does that do? The higher the molarity of the acid, the more hydronium will be produced at equilibrium. However, if experimentally, when we increase the acid concentration, we can measure and calculate that the percent ionization actually goes down. What does that tell us? That tells us that as we increase the acid, so again, recap, as we increase our acid concentration experimentally, percent ionization goes down. However, we know if we increase our acid concentration, we're going to make more hydronium at equilibrium. So what this tells us is that the increase in hydronium concentration is slower than the increase in acid concentration. So as you increase your initial acid concentration, you do not directly increase the hydronium concentration on that same level. Okay, let's look at finding the pH of mixtures of acids. So in general, we can ignore the contribution of the weaker acid to the hydronium concentration at equilibrium. And remember, it's this hydronium concentration at equilibrium that we need to calculate our pH. So if we have a mixture of a strong acid and a weak acid, the complete ionization of the strong acid provides more than enough hydronium to shift the weak acid equilibrium to the left so far that the weak acid's hydronium is negligible. So let's look at this a little bit more. So remember our weak acid, we have our HA, and if it's a weak acid, so any generic weak acid can be represented with HA. What is that acid hanging out in? Water. So our equilibrium relationship is between HA and H2O. Equilibrium arrows because it's a weak acid, so it does not dissociate 100%. We're going to make some conjugate base A- and hydronium. So if we think back to chapter 14 with Le Chatelier's principle, what happens as I increase the concentration of hydronium? So if you increase the concentration of a product, remember your equilibrium will shift left. So if we have a strong and a weak acid, the strong acid dissociates 100%, produces a relatively large amount of the hydronium, shifting the weak acid equilibrium even more to the left, making the contribution of hydronium from the weak acid insignificant. And that's what this point is telling us. So if we have a mixture of weak acids, generally you only need to consider the stronger of the weak acids for the same reason. And a little caveat, as long as one is significantly stronger than the other and their concentrations are small, which is pretty much what we're looking at. So if you have a mixture of acids, you want to just only look at the strong acid to calculate the pH. You can ignore the second acid. Two scenarios. One acid is strong and the other is weak. Focus on the hydronium concentration produced from the strong acid. You've got two weak acids. Focus on the hydronium concentration produced by the stronger of the two weak acids. Okay, so let's apply this concept to a practice problem. So practice exercise 11. Find the pH of a mixture of 0.15 molar hydrofluoric acid and a solution of 0.1 molar HClO2. And I actually changed this to HClO because I wanted to use this Ka value. So update your notes if you have the slides printed out. Okay, so we have a mixture of two weak acids, HF and HClO, similar molarities. So how do we get the pH? Well, we have to figure out which of the two acids is stronger. So hydrofluoric acid, HF, has a Ka of 3.5 times 10 to the negative 4th. HClO has a Ka of 2.9 times 10 to the negative 8th. So we have to determine which acid is stronger. Well, I know that the larger the Ka, the stronger the acid. So I see that the Ka of HF is larger, therefore HF is stronger. So we can essentially just ignore the contribution of the H plus from HClO and focus only on the HF produced at equilibrium, or the hydronium produced at equilibrium from HF. So what I want you to do, I want you to go ahead and look at this problem on your own. I'll get you started. So essentially, once you figure out that you only have to look at the HF, this becomes calculate the pH of a weak acid. I have some notes on the next slide. So remember, to calculate the pH, number 1, write the hydrolysis reaction and the Ka expression. Number 2, ICE, plug it in your initial values. Change is minus x plus x. E is I plus C equals E. Point 3, think, how do I solve for x? Essentially the same 3 points. So go ahead, pause, work on this problem, hit play again, we'll go over it together. Okay, so thank you for pausing. We are now going to go over how to get the pH of a solution of HF. We're ignoring the HClO because it's a weaker acid, so it's not going to change the pH significantly. Number 1, your hydrolysis reaction. So HF, you could also use HA, the generic acid, either one is fine. HF plus water, we make hydronium and a conjugate base, fluoride. Ka expression, hydronium, times fluoride, so right, products divided by reactants. And remember, we're multiplying these together. Point 2, ICE, where you plug in your initial values. Nothing is mentioned about hydronium or fluoride, therefore there is 0. The change, minus x plus x plus x. Again, there's no number in front of the x's because our mole ratio is 1 to 1 to 1. And equilibrium, I plus C equals E. Water, again, is not involved in the Ka expression. We don't need to consider it for our icebox, so I just like to put an X down there. So now we're at point 3. Think, how do I solve for X? Well, remember, we were given on the previous slide, or you would have looked it up in your textbook if it was a problem, on the front of your exam if it was a test, that Ka numerical value. So we're given Ka, which is 3.5 times 10 to the negative 4th, so that's how we're going to solve for X. Because remember, Ka is products of a reactant, that's just X times X, which is X squared, divided by our reactant, 0.150 minus X. And now we're going to use our shortcut. Remember, we want to assume that X is 0. Why do we do this? So we can avoid the quadratic formula. And this is true when Ka is small and your acid molarity isn't super small. So taking x to 0, I get 3.5 times 10 to the negative 4th equals x squared over 0.150 minus 0. So now we have this. Now this algebraically is just 1 minute problem to solve. Algebraically solve for x, multiply both sides by 0.15, take the square root. So we got 3.5 times 10 to the negative 4th times 0.150 to the 1/2 power, which is the same as the square root. And I now solved for x is 2.2 times 10 to the negative 3rd. Again, make sure you can get that on your calculator as well. So now we've solved for x. We want to make sure this assumption is true. We want to check, is x really small compared to the number it was being subtracted from? So I take x divided by the number it was being subtracted from times 100 to check our 5% rule. So x over 0.15 times 100. Again, x I got as, oops, that should be a 2. Let me update that. 2.2 times 10 to the negative 3rd divided by 0.15 times 100, and I got 4.8%. Let's go ahead and double check with that 2.2. It might be a little bit different. I'm not sure what I typed in my calculator last time. 2.2 times 10 to the negative 3rd divided by 0.15 times 100. 1.46, so this is even smaller. So essentially 1%. So x is indeed small. So as long as x is 5% or less of the number it was being subtracted from, we can go ahead with this shortcut and avoid the quadratic formula. Okay, so now we've solved for x. We have to figure out if we answered a problem yet, and the answer is no, because the question is asking for our pH. We have x, so again, using your icebox that you set up with your reaction up top, ICE on the side, I see that X represents my fluoride molarity, which I could have asked for, the fluoride molarity. But it also represents the hydronium molarity at equilibrium. And remember our pH equations. pH equals negative log of hydronium. Hydronium is my X, which is that 7 point, I don't know if it's 7.2 or 2.2. Regardless, 2.2, 7.2. Negative log of hydronium molarity equals 2.14. Let me check my notes. It is indeed 7.2. So my typo was here. I can't erase. But, so this was correct before the, there we go. So, this typo is right here. Apologize. This is a 7. So, the 5% rule is still met, and my pH is negative log of hydronium, which is 2.14. Okay, practice exercise 12. Similar concept, a slight twist. See if you can figure it out on your own. Here it says determine the pH at 25 degrees Celsius, and that just tells us that our Kw value of 1.0 times 10 to the negative 14th is valid, of a solution that is a mixture of 0.045 molar HCl and 0.15 molar HF. Okay, so a mixture of acids, remember what you want to figure out, which of the acids is stronger, and solve for the pH of that acid. Ignore the weaker acid. So go ahead, hit pause, think about this problem, solve it, hit play. We'll go over it together in a few minutes. Okay, so here we are again looking at our mixture of acids. I see that HCl is a strong acid, HF is a weak acid. So what do we have to think about? We could ignore the HF because it's our weak acid. And we can only consider the HCl. It's a strong acid, so do we need an ice box to get the pH of a strong acid? The answer is no. It's a strong acid. It completely dissociates. There's no equilibrium. There's no Ka. Remember then our 0.045 molar HCl solution gives us a 0.045 molar H+, which is what we need to get our pH. And that's again because it's our 1-to-1 mole ratio. We went over this in class and lecture about a week ago. So our pH equation equals negative log of H+. That's the negative log of 0.045. Again, typing that into your calculator, 1.35. Thinking about sig figs, 2 significant figures here gives us 2 digits past the decimal point. Okay, so now we've looked at calculating the pH of strong acids, of weak acids, of mixtures of strong and weak acids, or 2 weak acids. Now we're going to shift gears and we're going to look at strong bases. So the second half of the chapter, we're going to look at bases strong and weak. So for strong bases, remember they can dissociate 100%. That's what we're looking at here. How do you know what bases are strong? Remember there's 6 strong bases. They're listed on the chapter 15 equation sheet. You do need to memorize them. They're essentially all of our soluble metal hydroxides. So a metal hydroxide, soluble means it goes into water, completely dissociates, which is the definition of a strong species. So the stronger the base, the more willing it is to accept an H+. So think about our strong base hydroxide. Hydroxide really wants to grab an H+ to turn into water, which is much more stable, less reactive. For ionic bases, practically all units are dissociated into hydroxide or accept H+. So strong bases are strong electrolytes, meaning for every 1 mole of a strong base you put in, it completely dissociates into 1 mole of the cation and 1 mole of hydroxide. Conducts an electrical current. So how do we get our hydroxide molarity? It's just the molarity of the strong base times the number of hydroxides that we have, and that's just our mole ratio that we're looking at there. Okay, so for calculating the pH of strong bases, we'll have some practice in workshop this week and on mastering chemistry. Pretty straightforward. We're going to go ahead and jump straight into weak bases. So weak base, what does a weak base do? It dissociates less than 100%. A weak base, really common weak base, ammonia. We've looked at this reaction a bunch in lab and in workshop. It accepts the proton from water to make the conjugate acid ammonium, left with the conjugate base hydroxide. So if you have ammonia in a beaker, what is actually in that beaker? What would you see if your eyes are microscopic? You'd have some NH3, still just as NH3. You'd have some NH4+. You've had hydroxide, and you would also have, of course, water. So in this species, in this beaker, what species is going to determine the pH of the solution? Is it the ammonia, water, ammonium hydroxide? Well, it's going to be our hydroxide because that, remember, is our strong basic ion. And it's an equilibrium reaction, so our equilibrium constant expression is going to be Kb, because now we're looking at a base reaction. This is called our base dissociation constant. Been looking at these since chapter 14. Products over reactants, again, leaving out water because it's the liquid. So Hb, which in this case is our ammonium, any of the conjugate acids, divided by hydroxide, Hb, the conjugate acid, times hydroxide divided by that weak base. So here we're looking at the specific reaction of NH3. You could also look at a generic reaction where we're looking at our base, we'll just call B-. Could be any species you want for the generic base. And it's going to react with water. And this is a weak base, so we have an equilibrium reaction. So the base accepts a proton to make our Hb. Remember, the proton comes in as an H+. So B-, once it's protonated, is neutral. And then water is left with our OH-, the conjugate base. So here we have a generic base reaction in the Kb. Dissociation constant there. Okay, so here's a list of some common weak bases. Ammonia, right, NH3, pyridine, hydroxylamine, methylamine. So what's common with these first three species? They all have nitrogen. And with that nitrogen is a lone pair. So common for the weak bases, NH3 is a common weak base. So NH3 is the common weak base. Nitrogen is frequently found in weak bases. What makes it a weak base? The fact that that nitrogen lone pair can accept an H+. Okay. And then a couple others. The hydrosulfide ions, you could imagine that S could accept a lone pair. Carbonate ions, so one of the external oxygens to make the conjugate acid HCO3. And another example, hypochlorite to make HClO. Our base reaction, which you can write, and the Kb value, which is provided in a table, or you could be given a molarity and a pH and you could calculate it. So for this first practice exercise, which of the following compounds should produce the highest pH as a 0.05 molar solution? So highest pH means it's going to be the most basic. So we're looking at pyridine, which is right here, methylamine, which is right here, and nitrous acid. Okay, well, highest pH means most basic. So right away, I know nitrous acid is wrong because it's an acid, so it's going to have the lowest pH. So now between pyridine and methylamine, which is going to have the highest pH, which will be the most basic, we can look at the Kb value. So pyridine has a Kb of 1.7 times 10 to the negative 9th. Methylamine, 4.4 times 10 to the negative 4th. So which is a stronger base? That's right, it's the Kb that is larger. So that means that our methylamine is a stronger base. It will produce more hydroxide, right? So larger K value, more products are formed. It'll produce more hydroxide, which will give us a higher pH, or the most basic solution. So the answer here is methylamine. Okay, so now let's go ahead and look at practice exercise 13, finding the pH of a basic solution. So in this question, we're asked to find the pH of a 0.15 molar solution of NH3. Okay, so you want to think, this is a base. Is it strong or is it weak? If it's strong, remember strong acid, strong base, you do not need an icebox. Weak acid, weak base, you do. And we should all remember very easily that NH3 is a weak base. So how do we get the pH of a weak base? The same way we get the pH of a weak acid. Here we have our reaction, NH3 plus water to make ammonium and hydroxide. And the Kb value is provided, so 1.8 times 10 to the negative fifth. So I want to get you started. Again, number one, write your hydrolysis reaction Kb expression, which we saw in the previous slide. Number two, ICE. Number three, think, how do I solve for X? And then once you get X, think, how do I solve for pH? So go ahead, hit pause. I'm going to actually pause the video myself. And then we'll come back and go over the problem together.